Welcome back. We're quickly closing in on our first major goal for this course, to understand the structure of atoms and how those structures lead to the phenomenon of chemical bonding. In just a few hours together, we've investigated over 2 centuries of human debate over the existence of elemental substances and how they combine to form the rich library of materials that make up our world. We've seen how chemists in the early 1900s were beginning to get a solid read on the forces that drive chemical bonding. We've also seen how our understanding of electron pair repulsion and orbital hybridization helped lead to a proper understanding of the geometric relationships of atoms and molecules. This so-called hybrid orbital theory offered by Pauling seemed to complete the puzzle of predicting the geometries of molecules, which in turn allows us to predict some of their properties. But we aren't quite done. As useful as our theories about bonding, valence shell electron pair repulsion, and orbital hybridization theory are in predicting the properties of substances, they can all be put to shame using one of the simplest molecules of all, oxygen. It's hard to believe, isn't it, that this simple, well-understood diatomic molecule, one that makes up more than 20% of the air we breathe, can defy explanation using all of our previously discussed theories. In many ways, oxygen behaves itself in the face of these theories. For example, it contains the double bond predicted by our bond theory. Its atoms have no formal charge, just as the Lewis structure predicts. The bond length and strength between the 2 oxygen atoms is consistent with Pauling's measurements and hybridization theory also. So far, everything seems to be adding up. But oxygen has one property that can't be explained by any of these. Oxygen is attracted to magnets. That's right, oxygen is one of a class of materials that we call paramagnetic materials. Now, probably the most familiar material with this property is metallic iron. Take a sample of iron and place it near a magnet. That sample is attracted by that magnet. Paramagnetic materials like iron are attracted to magnetic fields because of unpaired electrons in their electron clouds. And this is easily explained in the case of iron because the 3 d electrons in the electron cloud are unpaired. Now, this is in accordance with Hund's rule, which dictates that degenerate electrons must occupy their own orbital whenever possible, maximizing spin. So, the paramagnetic nature of iron is no mystery to us. But in 1847, famed researcher Michael Faraday reported that strange observation, that oxygen was also attracted to magnetic fields, just like iron. We're back in the lab to demonstrate that oxygen is paramagnetic, that crucial observation Faraday made that led us to have to rethink how molecules are put together. Now, to do this demonstration, I'm going to use a few familiar materials and some that aren't so familiar. We're going to be using liquid nitrogen. Most of us have seen at some point. Liquid nitrogen is an extremely cold liquid, of course, but it is also colorless. I have a test tube of it here so you can see that. And I'm going to be comparing its behavior to that of liquid oxygen, which I've got in another test tube here. So if I hold them up individually, you can clearly see the liquid oxygen has sort of a pale bluish color. So these are 2 very different liquids, in some senses at least. And we're going to see how they interact with this magnet. Now, this permanent magnet that I have here creates a field of about 2.5 Tesla, which, to put things into perspective, is about 2 to 3 million times stronger than the Earth's magnetic field. And it's strong enough that when I pour these gases into the gap, if they're paramagnetic, they'll be suspended within the magnetic field that's generated at that point. So that's exactly what I'm going to do right now. I'm going to cool the magnet down first using a bit of liquid nitrogen. Then we're going to try the liquid nitrogen in the test tube and see if a stream of it will actually get trapped inside the magnet. And then we'll move on to oxygen and see if it behaves any differently. So let's get started now. Okay, now I'm going to be sure this magnet is nice and cold just by giving it a little bath in liquid nitrogen. I'm also giving my feet a little bath in liquid nitrogen, which is making them a little chilly as well. All right, that should be enough. All right, now for the test. We'll pour a little bit of this liquid nitrogen from the test tube very carefully through the gap. As you can see, not a whole lot happened there. It simply fell straight through under the obvious influence of gravity, but totally unaffected by the presence of this extremely powerful magnet. Now for the critical observation. We're going to do the same thing, but we're going to do it using our liquid oxygen. And just to be sure, I'm going to cool my magnet down one more time with a little bath of nitrogen. And again, pour the liquid, but this time, liquid oxygen. Quite different behavior, isn't it? So the liquid itself is trapped in between the two poles. That's not stuck because it's frozen there. That's stuck there because the magnetic field is actually holding it in place. And if there were any doubt that it's actually oxygen here, I can use this little ember to demonstrate. It most certainly is. Oxygen is accelerating the combustion of the fuel from the wood. So our demonstration proves that oxygen is what we call paramagnetic, which means that, although it has no permanent magnetic dipole of its own, it is attracted to other permanently magnetized objects, like the magnets in our demo. We reach an inescapable conclusion in the face of this observation. Oxygen must have unpaired electrons. Now, this probably didn't vex Faraday very much, since he couldn't possibly have postulated this. The electron itself hadn't yet been discovered. But as our understanding of atomic and molecular structure advanced even further through the early 1900s, it became more and more clear that unpaired electrons were almost always found in paramagnetic materials. So, what about oxygen? In every Lewis structure we have drawn so far, there has never been any indication of an electron without a partner. Based on everything we know right now, oxygen should not have this property. So what's going on? Well, remarkably, the answer to that question would have to wait until 1933, when Friedrich Hund and Robert Mulliken brought their intellect to bear on this problem. Hund and Mulliken had asked an even simpler question. If electrons can exchange places within an atom's electron cloud, as hybridization theory requires, can they exchange places within a molecule as well? In other words, is it possible that an electron in a molecule could move through larger regions defined by combinations of overlapping atomic orbitals? They found that the answer to this question is yes, and they dubbed these larger combined spaces molecular orbitals. Now, this expansion of hybridization theory would be bound by some of the same rules, most notably that the number of atomic orbitals put in equals the number of molecular orbitals that come out. But newly formed molecular orbitals are not necessarily all of equivalent energy the way that our hybrid atomic orbitals were. When adding atomic orbitals together across entire molecules, the complex geometric overlapping that takes place creates a set of molecular orbitals which can be very different from one another, in fact. So let's implement Hund and Mulliken's theory using a graphical representation of the space defining molecular orbitals and their energies. Consider the simplest possible molecule that we can consider. H2, right? The dihydrogen molecule. In order to create the molecular orbitals, let's first think of these hydrogen atoms as being separate from one another. They haven't bonded yet, which means that each of these hydrogen atoms has a 1s subshell with a single electron in it. Now, we all know that these electrons aren't moving in perfect orbits like this, but I placed them there just so that we can keep track of them. So we know that each has a single 1s electron. All right, I don't want to get emails about this. Now, let's put those two hydrogens together and see what happens when these orbitals combine. Now, molecular orbital theory tells us that they should combine in one way that creates a more stable system overall, a molecular orbital that's more stable than isolated hydrogen orbitals would be. And it looks like this. Now, why is this more stable when hydrogens are bonded? Well, the reason is, if you notice the shape of this construct here that has formed, there's going to be more electron density in the center of that molecule, in between the two hydrogen nuclei, sort of screening them from one another. So this lowers the overall energy of this particular pair of electrons. But there's also a second molecular orbital that forms. Remember that we always count up all the atomic orbitals in, and we get an equal number of molecular orbitals out. So what about the second one, right? What about the other one? The other one is not a sigma, but a sigma star. So here are our hydrogen atoms again, with our fictitious electrons. I'll take those away for a moment and we'll combine them. Now the second way that these S subshells can combine looks like this. Now notice that there is a plane through the middle here where there's really almost no electron density, if any, right, at all. That means those electrons spend more time outside of the H2s. So they're not screening those nuclei from one another. They're not making it more stable. In fact, they're making it less stable. So if electrons occupy this so-called sigma star molecular orbital, they will actually destabilize the bond, make it worse than not being bonded at all. Okay, so let's analyze the energetics of that a little bit more carefully. Now, here I've plotted a diagram where I have energy on my vertical axis, and I placed the atomic orbitals of hydrogen right here in the middle. And you can see each one has a single electron in it. These are the 1s electrons. The energy of those orbitals is equal to the non-bonding energy. That means that anything that forms that's lower in energy is going to be a bonding molecular orbital, whereas any orbital that forms that's higher than this line here is going to be an anti-bonding molecular orbital. And the energetics of those sigma and sigma star molecular orbitals looks a bit like this. Our hydrogen atoms combine and their atomic orbitals join to become molecular orbitals that look like this. Remember the sigma and the sigma star. And their energies are one above and one below that non-bonding energy level. Now my job is to use the inventory of electrons afforded me from these two hydrogen atoms to fill that molecular orbital system and ask one very important question. Does it lower the overall energy of the system? If so, a bond will form. Let's do that now. We have a molecular orbital down here and we have two electrons. Well, they can go in there, right? Hund's rule, the Pauli exclusion principle still apply. These electrons are paired in the same orbital but have opposing spins. Well, I'm out of electrons now, aren't I? Which means that the overall energy of the system has decreased as a result of populating the molecular orbitals. What that means is a bond's going to form. Now, not only that, but I can calculate the multiplicity of the bond as well. The bond order in any molecule from its diagram here is calculated using the number of bonding electrons and the number of antibonding electrons. So in this case, I have 2 bonding electrons. I have 0 antibonding electrons for a balance of 2. And remembering that it takes 2 electrons to form a bond, this equation here tells me exactly what the bond order should be. In this case, 1. My molecular orbital diagram predicts that hydrogen will exist as a diatomic molecule with a single bond. And that is exactly what we see. Now let's go a step further. Let's consider helium. And what I'm going to do now is create the same molecular orbital diagram, and I put it in quotation marks this time because we know that helium doesn't do this, but we're about to prove why helium doesn't do this. If 2 helium atoms were to combine, the molecular orbital system would look very much like one for a hydrogen molecule. The difference here is that my helium atoms have got 2 electrons each. So when I use my total inventory of 4 electrons, I can populate a bonding molecular orbital which would appear to lower the energy. But I've got leftover electrons, right? I've got one here, I've got one here. I still have to put them somewhere. And the only place left to put them is way up here in the sigma star antibonding molecular orbital. So overall, you notice that, I have my back covering it, but you notice now that the energy of the system has gone back up. So overall, there's really no energetic benefit to populating a molecular orbital system for a helium-2 molecule. And that's why, when we calculate the bond order, we see that 2 bonding electrons minus the 2 antibonding electrons divided by 2 helps us to predict that there should be no bond whatsoever. And in the case of helium, that's exactly what we see. 2 helium atoms would prefer to remain isolated from one another and not bonded together. Now let's go even a step farther. Let's consider some second row elements. Now, second row elements have got p subshells available, and they can interact with one another in a more complex fashion. We have p atomic orbitals that can combine now. And remember, a sigma bond requires that those 2 p orbitals overlap end-on. So we can only do that with one of them. And the remaining p orbitals are going to have to settle for making pi bonds. What this means is that when we combine 2 p subsystems like this to create molecular orbitals, for example in fluorine, we end up with 6 potential molecular orbitals, but we have a lower energy sigma and we have a higher energy sigma star, but we've also got 2 pi bonding molecular orbitals and 2 pi star antibonding molecular orbitals to consider. So my system is still going to follow the same rules, Hund's rule, the Pauli exclusion principle, and so on. When I populate my sigma, then my pi star, then my sigma star with the available electrons from fluorine, which remember fluorine is a 2p5, I get the following. Well, that looks really great, doesn't it? I've got a grand total of 3 pairs that go into bonding molecular orbitals, dramatically lowering the energy of the system. But I'm not done yet. I've still got leftover electrons to consider. So let's put those in a home. The lowest energy home we can find for them, unfortunately, is not bonding. It's antibonding. It's the pi star. So those 4 electrons that go into the pi star destabilize and counterbalance some of that bonding force, but not all of it, because our calculation tells us this, right? Bonding electrons, well, we have a total of 6. Antibonding electrons, we only have 4. What this means is that when we run our calculation, we find that there's a pair of electrons in the bonding molecular orbitals that is uncanceled. And that means fluorine should exist as a diatomic molecule with a single bond. And it does. So molecular orbital theory correctly predicts that hydrogen will be diatomic, or a molecule consisting of 2 covalently bonded atoms. It also predicts that helium will be monatomic, existing as an isolated atom. It can also demonstrate that fluorine should be a diatomic molecule with a single bond joining the 2 fluorine atoms. But octet rule and our bond theory already predicted all of this. So far, Hund and Mulliken's work hasn't really contributed anything new, except for a different way of thinking about what was already known at the time. But the real advantage of molecular orbital theory becomes clear when we turn our attention back to oxygen, a molecule which so far has never appeared in this course as a molecule with unpaired electrons. No lens through which we have looked at it to date can explain why oxygen gas is attracted to a magnet. But we now have a new lens, molecular orbital theory. Let's consider the molecular orbitals of a dioxygen molecule, O2. Now remember, this is going to be using the p subshells of oxygen. Now remember, oxygen is a 2p4 element. That means that I'm going to have a grand total of 8 electrons to populate this molecular orbital system. And when I follow Hund's rule and the Pauli exclusion principle and try to find the most stable configuration, of course, I'm going to be able to put 6 of those electrons into bonding molecular orbitals, and that has the effect of lowering the energy overall. Now, this is where things get really interesting. In the case of oxygen, I have 2 electrons left. Right? I had a grand total of 8. I've already used 6, but I still have these 2. I need to put them somewhere. Well, where are they going to go? Well, naturally, they'll go into the pi star system, but how will they arrange themselves? This is the important question. Remember that Hund's rule says we want to maximize spin, and the Pauli exclusion principle says that we can't necessarily have 2 electrons with exactly the same 4 quantum numbers in atoms, and the same thing applies here. In other words, we can't put them both in the same orbital with the same spin. So in order to satisfy both of those, we've got to put them in separate pi star molecular orbitals. Here they are, both with the same spin, so spin is maximized, and they are not in the same orbital. Now, that's going to counter a little bit of the bonding, of course, the effect of the bonding molecular orbitals. So we have a situation where 6 bonding electrons are going to be canceled out only by 2 antibonding electrons, giving us a total bond order of 2, which we've come to expect from oxygen. But even more importantly than that, it explains oxygen's magnetic behavior, something that none of our techniques could do before. For reasons which may forever remain unclear, Hund was not named when the 1966 Nobel Prize was awarded to Mulliken for the development of molecular orbital theory, which was actually known then as the Hund-Mulliken theory. Now, maybe the reason is that Mulliken was MO theory's greatest champion, and one of his most epic sparring matches over the nature of the chemical bond was with the man who conceived its predecessor, Linus Pauling, the father of hybridization theory. Mulliken and Pauling famously took jabs at one another's theories in the literature, each championing his own model of the chemical bond as the correct one. Perhaps somewhat blinded by their loyalty to their own creations, these two bickered relentlessly through their careers, each refusing to acknowledge the utility of the other's theory. It was a classic debate, with Mulliken accusing Pauling of being too narrow in his interpretation of chemical bonds, while Pauling fired back that Mulliken's was too obtuse and ignored details at the atomic level. Of course, the truth is much clearer to chemists today, that both of these theories are just models. Each predicts the behavior of certain systems better in certain circumstances. It's very much the same way that a compass and the bark of a tree can tell you better which way is south under differing conditions. Similarly, MO theory and hybridization theory better describe chemical systems under different circumstances. In hindsight, today's chemists can look back on this chapter of chemical history and clearly see how Hund and Mulliken's creation expanded our understanding of molecular systems. It wasn't just its ability to explain the magnetic behavior of oxygen. It was also remarkably adept at explaining the properties of larger molecules, which Pauling's hybridization theory simply could not. Just take a look at this molecule. This is a molecule of lycopene that you might find in the leaf of a maple tree or the skin and flesh of a tomato. Lycopene contains a series of double-bonded carbon atoms making up most of its backbone. Now, while hybridization might predict that each double bond consists of two pairs of electrons trapped between two specific carbon atoms, MO theory allows all 22 of those electrons making up the double bonds to occupy a space throughout the molecule. These larger molecular orbitals all have differing energies, and as electrons move from one molecular orbital to the other, they absorb light of very specific wavelengths to accomplish the transition. When this happens, these molecules appear to our eye to be the complement of that color. In this case, the molecular orbital energies differ by just enough energy to absorb green light, making the compound appear red to our eyes. This is actually the color that we see in fall as trees break down the dark green chlorophyll in their leaves to prepare for a long winter. This lets the color of the other molecules in the leaf shine through, creating the burst of fall color with which we're all so familiar. So the next time you enjoy a beautiful deciduous forest on a fall day, keep in mind that what you're actually watching is a complex dance of electrons between and among molecular orbitals predicted by MO theory. In fact, this phenomenon is exploited not only by nature, but by man as well. It's been used by chemists over the past 150 years to design and discover a range of colored compounds used to dye fabrics, paints, and even the food that we eat. So let's sum up what we've discussed today. We started with an observation which could not be explained by any of the bonding theories that we have discussed so far: the paramagnetism of oxygen. And we talked a little bit about why this peculiar property is not explained by the work of Lewis or Pauling. Next, we met Robert Mulliken, champion of the molecular orbital theory and a staunch rival of Linus Pauling. We saw how Mulliken's theory expanded on hybridization, allowing many atomic orbitals to form multiple bonded atoms to mix, creating larger orbitals, which could span the entire molecule instead of being confined to just one chemical bond. We then explored the molecular orbitals of some very small, simple diatomic molecules, explaining why hydrogen is diatomic and helium exists as isolated atoms, and fluorine has a single bond. Then we tackled the issue at hand, the paramagnetism of oxygen. We saw how the molecular orbital energies in a diatomic oxygen molecule lead to the presence of two unpaired electrons in its most stable electron configuration. And then we took a few moments to try to appreciate just how massive and complex molecular orbital systems can become by looking at some compounds that most of us are familiar with as commercial goods, but may not have ever really thought of on the scale that a chemist might. We saw how molecular orbitals can play a role in the stability, reactivity, and even the colors of these kinds of compounds. And with that, we conclude our discussion on chemical bonding for now. Although we have finished focusing strictly on the phenomenon of bonding, As we continue through the course, I hope that you'll see how our evolving understanding of the forces holding atoms together has helped us to explain and even change the world around us. Next up, it's finally time to start making and breaking those chemical bonds that we have worked so very hard to understand. It's finally time to discuss chemical reactions. See you for that next time.